Welcome, patrons. This is Francis Tapon. This is a special podcast just for you guys. I interviewed Jack from the NASA Ames Research Center. He is an astrophysicist. This podcast will probably not be released to the public because I was recording this interview for a website called Underknown.com. And I know they were going to hack the audio and video that I recorded to death, and that only a fraction of it would be shared with the public. But I thought, my patrons would absolutely love hearing this entire interview with one of the foremost authorities on terraforming in the world. So it's kind of geeky, I suppose. If you like astronomy, you'll love this. Enjoy this special episode just for you guys.
My name is Jack Lissauer. I'm an astrophysicist. I work at NASA Ames Research Center studying problems in our solar system and other planetary systems. Tidal forces are the result of the finite sizes of bodies, and that gravity acting on the near side of a body is stronger than that on the far side. We're familiar with tides because of ocean tides. Ocean tides result of the pull of the moon and the sun on Earth being greater on the near side than on the middle of Earth, and greater on the middle of Earth than on the far side. They stretch out Earth along the directions of the Earth-Moon line and the Earth-Sun line. Now, Earth we think of as a solid body, but on large scales, it's not completely solid. And what we think of as a solid Earth gets stretched out, but as you might well suspect, water in the oceans gets stretched out much more easily, and thus the tidal effects on the oceans are larger than the tidal effects on the shores, and therefore there's a bigger tidal bulge in the oceans, and that's what we commonly see when we look at tidal tables. And the reason that tides on Earth depend in amplitude on exactly where you are is the flow of water and the relative patterns of the water and the land. Tides are also important for other bodies in the solar system, and in particular for our moon. The reason that we always look at the same hemisphere of the moon is because tides have slowed the moon's rotation such that the moon's rotation is synchronous with its orbit about Earth. Now, tides are also slowing Earth's rotation and causing the moon to move away from the Earth at the rate of about an inch a year. How do we know that? We know that from several different sources. The simplest way to think of it is by direct measurements, because the Apollo astronauts left laser retroreflectors on the moon as part of the science packages. And these have been used to measure the precise distance, and it's increased by an average of about 1 inch per year over the past few decades. But there are other measures. One other measure is as the moon is moving away from Earth, the Earth's rotation is slowing. only slowing a very little bit, but enough that if you go back and look at the historical records of the times and locations of visibility of eclipses back in ancient days, such as the time of the Roman Empire, you can see that you can fit the observations when you include the recession of the moon and the slowing of Earth's rotation. So the Earth was rotating a little faster back then. A day was a little shorter. Now, you can also see evidence of this on much longer timescales in the fossil records. There are certain organisms, fossils of bivalve, sea-dwelling animals that had growth patterns that were affected both by the day-night cycle and by the seasonal cycle. And by seeing these two types of variations, you can see how many days per year there were back when these organisms lived, which was a few 100 million years ago. And they found that for the particular organisms that I'm thinking of, it was just under 400 days per year, so 399 point something. I forget the exact number to be precise. This, of course, is significantly more than what we have now. And the year hasn't changed. It's the length of the day has gotten longer. Now we see evidence of tides elsewhere in the solar system. If you look at the rotation rates of the planets, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all have rotation periods, essentially days, that are between 9 hours and 25 hours in length. But the two closest planets to the Sun, Venus and Mercury, have much longer days, well over an Earth month. And this is because just as the Earth has slowed the rotation rate of the moon due to tides, the Sun has slowed the rotation rates of Mercury and Venus. The exact rotation rates of these two planets are not equal to the orbital period for fairly complicated reasons that are different for the two planets. In Mercury's case, it has to do with an intrinsic asymmetry and the eccentricity of Mercury's orbit. In Venus's case, it's due to the heating of Venus's massive atmosphere, also by solar energy. A lot of people say that Venus is the only planet that rotates retrograde, in other words, in the opposite sense from which it orbits. But this actually isn't true. There's another planet that rotates in the retrograde sense, the planet Uranus. Now, Uranus really rotates nearly on its side, but it's rotating slightly backwards, not exactly on its side. There is considerable disagreement on the origin of planetary rotation. Most people think that large planets that are primarily gaseous, like Jupiter and Saturn, are rotating in the forward or prograde direction because the way the gas came in and they accreted that gas. And if that's the case, then the vast majority of planets like them, gas-dominated planets that are far enough from their stars that tidal forces would not have slowed their rotation, would be expected to rotate in the prograde or forward sense. There's a lot more uncertainty about terrestrial or rocky planets like our Earth. It's thought that probably the majority of them also rotate in the prograde sense. but that a significant fraction are retrograde. With planets close to the star, most of them, again, are likely to be prograde, regardless of their compositions, because of tidal forces from their stars. If Jupiter disappeared from our solar system suddenly, then over time, the Earth would be bombarded with substantially more comets than it is today. People have used this to speculate that you need a Jupiter in order to protect terrestrial planets from comets. This isn't necessarily the case because of two reasons. One, a lot of that protection would still exist if a Neptune-mass planet were there in Jupiter's orbit. And the second thing is the comets were placed where they are at the current epoch, largely, we think, by perturbations from the giant planets, especially from Jupiter and Saturn. So if it hadn't been there from the beginning, there might not be those comets. If the Earth were suddenly moved into the orbit of Jupiter, then Jupiter would no longer protect Earth from cometary bombardment. And if Earth were orbiting at a substantial distance comparable to that of Jupiter's outer captured irregular small satellites, then those comets wouldn't impact at that high a velocity. They would be mainly pulled in by Earth's gravity. However, if Earth orbited Jupiter close in, similar to the orbits of the 4 large moons discovered by Galileo more than 4 centuries ago, then the flux of bodies would be increased and Jupiter would have pulled them in. They would have fallen into Jupiter's gravitational field and be moving faster. And that's especially true if Earth were in the orbit of the closest Galilean satellite, Io. Let's imagine a solar system in which you have a planet very similar to Jupiter, orbiting at Earth's distance from its star, and it has one moon, which has the same mass and composition as our Earth. First of all, if the moon of Jupiter, the Earth-like moon of Jupiter, were orbiting in the retrograde direction for some reason, then it would quickly spiral into Jupiter, unless it was pretty far away. If it was rotating in the prograde direction, then it would spiral out, unless it was pretty far away. But it would probably go outward, but not too far. I think it would still be maintained in the orbit around Jupiter, and in many respects, it might be very similar to the Earth that we have today. One difference is that its rotation would likely be tidally locked. That means its rotation rate would be equivalent to the orbital period of the planet around Jupiter. That would have to be weeks or months. If it were less than a week, or even probably 2 or 3 weeks, then the tides that Earth raised on Jupiter would cause the Earth to spiral out farther. If it were longer than a few months, it wouldn't be stable in orbit around Jupiter. It would go around and escape and go in an independent orbit around the star, maybe colliding with that Jupiter, maybe being ejected from the system, probably one of the two fairly soon. So what would the differences be? The first difference, as I mentioned, would be that the day would be longer because the rotation period would be slower. Another difference is that sometimes it would go behind Jupiter. And it might do this once every orbit of Jupiter. Now, those people who've experienced a solar eclipse, be it a total eclipse or a partial that was almost total, realize that it gets a bit chilly, or it can. But this is our little moon barely blocking the solar disk and totally blocking the solar disk at this point for no more than 7 minutes and a few seconds at a time. And just a little bit of the Earth is in the moon's shadow at any given time. Well, in Jupiter's shadow, Earth would be traveling for a period of perhaps several hours and perhaps once every month. This isn't just night, it's night for the whole planet, so it cools off. The climate regime would be different. In addition to just having the rotation period different, which would mean that the cyclones would be less severe. The other thing is the magnetic fields. And this is complicated and depends on exactly how far the Earth was from Jupiter and what the Earth's magnetic field was and how many particles got trapped in Jupiter's magnetic field. Earth would be certainly going through Jupiter's magnetic field at times, magnetosphere. It might be in it for the whole time, depending on how big the magnetosphere of Jupiter was and what the size of Earth's orbit around Jupiter was. And it's possible that there'll be a lot of charged particles gradually eroding the atmosphere, perhaps most severely during times when Earth's magnetic poles flipped. But Earth's magnetosphere might be significantly different than it is today anyway, just because of the slower rotation rate of Earth, and that affecting the Earth's internal dynamo, which is generating the magnetic field. Now, everything I said up to now assumes that Earth was the only major satellite of this Jupiter-like planet orbiting in the star's habitable zone. If there were two Earth-like planets, the one closer to Jupiter would be pushed out harder, just like Io is pushed away from Jupiter more strongly than the other Galilean satellites today. And eventually, the inner planet would probably come up to an orbital resonance with the other planet. And this is a case where the inner planet would orbit twice for every time the outer planet orbited once, or perhaps if their orbits started closer than a factor of 2 to 1 in orbital periods around Jupiter, orbited, say, 3 times every time the outer or satellites orbited twice. Now, these type of orbital resonances under many circumstances are stable, but Jupiter will be pushing on the inner planet, the inner Earth, much more than the outer Earth. And for them to remain in lockstep, the inner Earth would have to transmit energy and angular momentum to the outer Earth. Well, it could do this gravitationally, but there's something, a little subtlety, that I haven't mentioned because it hasn't been important up to now. If you have one satellite orbiting. And it's raising tides in the primary body. Those tides cause it to be pulled away, but they cause it to be pushed away in the same way, in such a way that its orbit does not become more or less eccentric as a result of this force. It's given the energy and angular momentum in just the right proportions to expand an orbit which, if it starts nearly circular, will remain nearly circular. But that proportionality is different at different distances from the planet. And it's such that there's more energy for a given amount of angular momentum close to the planet than far from the planet. So if a satellite close to the planet gives energy and angular momentum to a satellite farther from the planet, you have excess energy for a given amount of angular momentum. Where does that excess energy go? It goes into the orbits as eccentricity of one or both of those satellites. Now, in the case of Jupiter, we have 3 satellites in resonance. The inner one, Io, is the most volcanically active body in the solar system. That's because in keeping this resonance, Io's eccentricity is excited, but Jupiter is able to then change its tidal forces on Io as Io moves in and out in its eccentric orbit. And this flexes Io, causes a lot of dissipation, melting in the interior. And this would happen in the Earths. Maybe mostly the inner Earth, probably mostly the inner Earth, but it could be mostly the outer Earth, or it could be some of each, depending on the particulars of the resonance. And that would make the Earth analog orbiting Jupiter much hotter in terms of its internal energy, much more volcanically active. Would it make it uninhabitable? Perhaps, probably not. But it would certainly be a difference. And indeed, if you actually had these Earth's analogs at the Jovian distance, 2 of them, not just one, but you could have a thriving biosphere under the surface, if you could start one. And starting one is more difficult, because that may require something like the huge amounts of excess energy, free energy available from the radiation of the star. If you moved Earth to Jupiter today, it would quickly cool off, but Earth is a fairly big planet, and you'd have some subsurface energy, and you'd have a biosphere, being able to survive underground for fairly long amounts of time. The surface biosphere would quickly cool off, freeze, and be gone. If you took Earth and put it around Jupiter now, then, of course, the sun would be much fainter. There'd be a lot less energy input in our biosphere from solar radiation, and the atmosphere would quickly cool off. If you put Earth into an eccentric orbit around Jupiter, especially an eccentric orbit close to Jupiter, then tides raised by Jupiter would cause a lot of internal heating and extreme volcanic activity. Even if you put Earth in a circular orbit, if it was close to Jupiter and not rotating at the same periodicity that it orbited Jupiter, there'd be substantial tidal forces that would cause a significant amount of tidal heating. But in either case, if the Earth were the only really massive satellite Jupiter, that tidal heating would be temporary and would last for a time period very short compared to the age of the solar system or to the amount of time that life has flourished on Earth, even just advanced life or animal life specifically. That doesn't mean the Earth would freeze over deep down. There would still be the internal heat of Earth. There would still be radioactive decay, so the deep biosphere would survive for a long time. If you didn't place just one Earth, but you placed, say, an Earth and another planet, a Venus, for instance, whatever, a second Earth, around in the same orbits that the two of that Io and Europa occupy, or maybe better, Europa and Ganymede occupy, resonant orbits, then you'd have a situation where tidal heating could last substantially longer for the same reason it lasts for a long time in the Galilean satellites. Now, this tidal heating by itself wouldn't probably be enough to power a substantial biosphere. But actually, at that point, you'd have a case that tidal heating might allow liquid water on the surface and a significant atmosphere and the sunlight, 1/30th that we receive on Earth, but still, so not enough to provide enough energy to keep the planet warm, but enough energy to have some photosynthesis, to have more of the free energy, the energy useful for life as we have it on Earth today, could allow life, somewhat complex life, to survive if everything just were in the right spot for a much longer period of time. The moon probably does have a tiny liquid core, but that's not needed because it's still flexed, and the moon is getting slightly heated now. It's slightly heated because its distance from Earth, it's on an eccentric orbit around Earth, but it's pretty far from Earth. Earth is pretty small, and it's not that eccentric. And crucially, its orbital period its rotation period is synchronous with its orbit. So there's no rotational energy to be damped. It's only the eccentricity, the excess energy of the eccentricity for the angular momentum of its orbit that could be damped. And it's slower, indeed, because the moon is fairly rigid and therefore is not as mushy as Earth. And indeed, if you look at the history of Earth and how quickly the Earth is slowing down in its rotation as a result of the tidal forces from the moon, if you extrapolated back in time and accounted for the fact that the moon would have been closer to Earth and therefore stronger tides, you would have the moon back near Earth less than 2 billion years ago, very close to Earth. But we know that there are rocks on the moon that are 4 billion years old, over 4 billion years old, and rocks almost that old on Earth. And this was a conundrum for decades until scientists finally realized that the reason the moon is going away so rapidly at the current epoch is because of sloshing of water that is tidally perturbed by the moon, and the amount of sloshing depends largely on the configuration of the seas, and especially the shallow seas. Think about waves crashing on the beach. Those type things are what's dissipating the energy within the Earth and causing the moon to recede. If you want to live on a world other than the Earth, as a human being, we're talking about, then the easiest place to put an isolated environment would be probably on Mars. Maybe the moon simply because it's closer, but Mars because it has some atmosphere, it has a little more protection from certain things than our moon. There are locations in the atmosphere of Venus where it's not too hot, but they're high up. Staying up there is much harder than being on the ground on the moon or Mars. You need to have complete isolation from the atmosphere. You need to protect yourself from all the energy coming from the sun and from the surface of Venus. And it's much harder to air condition to cool than it is to heat. So Venus, terraforming Venus, making it habitable for people, is something that could be done. It requires two things: adding water and keeping sunlight away. What you could do is perturb very slightly some of the large minor planets, small bodies, ones that happen to be in orbits that are very close, that may come not that far from some of the giant planets, the so-called centaurs, whose orbits cross the giant planets. Perturb one, get it to go by the giant planets enough times in the right way that it smashes into Venus. And you do that with a few of these. You don't get an ocean's worth of water, but you might get many lakes worth. And then you provide shade, a star shade or sunshade for Venus to keep some of the energy coming in and hitting the surface, cooling the planet off. Now we're talking about thousands of years probably. With current technology or envisioned technology for this century, we're probably talking about thousands of years to get it in that shape. But it could be done. And because Venus's mass is similar to Earth, and as long as you kept that star shield up, you could keep it cool. You'd have to have a technological civilization. I don't know of any way you could get that star shield to be something that would last long term without regular maintenance. But it's possible. It's not, as I said, you'd have to keep in good shape. You couldn't have dark ages because then you'd be roasted and that would be it. So we'd have to have a more advanced civilization in a moral and ethical manner than we have, unfortunately, in the world today.
And that concludes this episode of the WanderLearn podcast, where we explore travel, technology, and transformation. If you'd like to see the show notes with links to what we talked about, or if you'd like to comment on the show, or if you'd like to ask me a question, then go to WanderLearn.com and click on this episode. If you'd like to connect with me, just remember Tapon. That's my first initial and my last name. Tapon is the username I use on all social media. You can also get to my website by going to ftapon.com. And here's one last reason to remember Tapon. If you like what I do and would like to get rewarded for supporting my projects, then go to patreon.com/ftapon. That's where you can pick up some remarkable rewards for as little as $2 a month. And now for 5 quick favors. Number 1, subscribe to the WanderLearn podcast. 2, download it. 3, share it. 4, review it somewhere. And 5, sign up for my newsletter at WanderLearn.com. Our theme music was composed by Eric Stratman. This is Francis Tapon, encouraging you to wander and learn.